Hello, everyone, and welcome to the November 3rd Geometro webinar. We're really excited to try this new way of a workshop out here with you guys. So you are the first ones to go through this. Congratulations. I'm very excited to have Aniceta Skowron, the creator of the Geometro here, and she's going to lead you through a series of activities to build with the kit that we sent you, and she custom made this kit just for this webinar series, so we're really excited. So you have a one-of-a-kind Geometro kit with you. The opening code for this session is going to be triangle. Triangle is the opening code. Okay, so I just want to make sure that you have your Geometro kit, that you have 2 dry erase markers, that you have scissors, and a nice, solid, clean area to work at. I know some of you are still troubleshooting some camera issues. I will be monitoring the chat box. If you need my assistance, I can work with you in the background while Aniceta presents. And without further ado, I'm going to turn it over to Aniceta. Thank you.
Okay, good afternoon, everybody. Welcome you to the first ever webinar for Geometro. We have never done that before, and I'm really excited for this tour de force. What I planned for this afternoon is to share with you some of my ideas on how to use Geometro with sometimes little additions, little props, to teach geometry concepts in an accessible way for your students. So here is the plan for the workshop. We are going to have 3 parts. First, we are going to just build some pyramid prisms and maybe something else, depends how timely we can do that. Then we will do some the major and the most important part of the webinar will be modeling of 3D problems and concepts. And then right towards the end, I would like to share with you some ideas on how to continue and what to do if we ever meet in person, so that you are excited and you know, like, can decide for yourself if all that is something that you would like to do. So what kind of problems are we going to be modeling? I will start with Euler Equation and labeling of the faces, vertices, and edges. Then we will go more into labeling and modeling of word problems, like showing and touching distances in solids, making Pythagoras triangles inside solids so that problems like word problems can be solved. I will show you how to, very quickly, how to relate to area, but more extensively, how to make volume accessible a little bit better. Then we will investigate and investigate diagonals in different solids. Then we will do some measuring of volume of pyramids and prisms. Then we will talk about nets, and if time is there, cross sections. So without further ado, we will start with building. So get your kits out and pick up pieces that are relevant to making this. So how about you just make this and raise your hands, or like Andrea will stimulate here to see how we are doing building this. Okay?
Okay, so get building, and I'm going to call on some people if I don't see some hands raised to share. And you can also go ahead and turn your video on while you're building if you like. That is not a problem.
Yeah, you have to pull out the pieces that are relevant. And I maybe forgot to say one thing. One thing only is very important here. You can see that the edges of all those polygons have hook and loop. So what you need to do is to touch hook to loop, loop to hook, like this. And it will stick. You don't need to overlay, you just touch. but it is important that you actually touch hook to loop, loop to hook, because if you don't, it will not stick, it will fall apart. So make sure that it's always hook to loop, loop to hook.
All right, perfect. So go ahead, Tori and Diane, go ahead and share your video. So you'll just have to click on the start webcam icon and then start, or I think it says start or share. All right, we got Diane, we got Tori. Woohoo!
Oh, super, wonderful. Now, Tori, what kind of polygon did you use for this, for the base? I cannot hear you, but I can see that, you know, you could examine this drawing here that I presented and compare with what you did.
And you accidentally used 6 sides instead of the 5.
Yeah, okay, so you made something a little different. And who is at below? Oh, wonderful.
Diane.
Diane, okay. So Tori made, what did you make, ladies?
Well, I guess I made a hexagon.
Yes, but the solid, what is the name of the solid?
A prism?
In geometry,
I don't know.
Prism, yes. And for one lady, it's a hexagonal prism, right? And for the other lady, it's a pentagonal prism, right? Yeah, exactly what I had on this drawing. Now, next exercise, what I would like you to do is to think of me being somewhere away on the phone. I cannot see you, you cannot see me, and I would like to get an instruction from you to build that solid. What would you say? What would you tell me? I just want maybe one person, you know, just saying out loud, maybe for everybody. What would you tell me if I were to ask for instruction to make that solid? I will follow your instruction. Anybody?
Other people, or do you want like one of us to do it?
Well, you already speak, so you can tell me.
Okay. Well, I can do that. Do you want me to still go off my hexagon, or do you want me to change mine to the other one?
Well, I want what is on the drawing.
Okay, let me find my other piece.
So what do I do? So here is another kind of idea for you. When student actually make some solids, it's a very good exercise to actually get them verbal about it, to say what they are making, how they are making it, because that gets them to actually articulate all those spatial concepts and relationships and such. Okay then, Tori, go on.
Okay,
what should I do?
Tell my student to find, they probably know the squares easiest, so I would tell them to get all their supplies ready. So they're going to have 1, 2, 3, 4, 5 squares.
5 squares, I
would
have some, yeah, okay.
The sides, because there's hard Velcro and soft Velcro. So I would tell them to find the other one that has like 5 pairs of Velcro. Maybe have them like count how many, just if I'm trying to be making them really independent. And then I would tell them to match the soft Velcro to the hard Velcro and put it kind of on top. Or to the side, I guess, and lift it up, however their fine motor skills are.
Yeah, but what would you say about the shape themselves?
Oh, I would tell them to take the square and put it, match it up to one of the sides on the hexagon. Or the Pentagon, sorry, I'm on the hexagon line. The Pentagon.
Pentagon. Okay, so maybe like this, right?
Mm-hmm.
And then?
Oh, then I would have them.
So you say, did you go all 5 already?
I don't know. It depends on the student. I would maybe have them do them all and then lift them up at the end. Or if they can hold them both at one time, because I know I can hold them both at one time and keep moving. Yeah, like that.
Okay, and once they have all 5, right, you would put another pentagon on top, right?
Yes.
Oh, and we have that. Super. That's the instruction that I usually get. That's a very brilliant instruction, very straightforward instruction. But I would like you to consider something different. And I would like to build the instruction on something else, some property of this solid. Now, if you look at that solid that's in front of you, you look at the vertex. Look at the vertex, any vertex of that solid, and you tell me what shapes, what polygons come into contact here at that vertex.
Mine is two squares come into contact.
Two squares? Just two squares?
Oh, sorry, with the one on top, yeah. Oh, man. My Pentagon touches my two squares.
Yeah, so you have two squares and?
The Pentagon.
Two squares and a pentagon, right here, right? Hang on, this way. Two squares. Here you have one square, second square, and hang on, I am seeing myself in the mirror, and a pentagon. So it's two squares and a pentagon. Is each vertex like this?
Yes.
Yes.
Yeah. Yeah? Okay, now, knowing that each vertex is like this, that has two squares and a pentagon, how can we use this idea to formulate an alternative instruction? Starting with the words, build me a structure. What would you say then?
Not quite sure what I would say. Just like to the student.
Anybody else? Yeah?
Would you say what you just said? Build me a structure where each corner connects two squares and one pentagon?
Exactly. Yeah, except that I would use the word vertex, but if they don't understand the word vertex, then it would be corner. But exactly this. Build me a structure that has two squares and a pentagon in each vertex. Right? Now, what are the advantages of this kind of instruction? Especially for you guys, especially for your students, is that they don't have to know what they are building, and they just have to locally look at every vertex, because they examine everything locally anyway. So here you have a local way of telling what to build. Now we are going to practice this, okay? So we are going to I will give you instruction, and you will follow that instruction. So you will build something that you not necessarily know what that is, but you will follow just the instruction, right? So here, make a structure in which one pentagon and three triangles meet at each vertex. So basically you have to destroy what you've done because you only have two pentagons, but that's okay. So make that and see how it's going. So look at each vertex, and at each vertex place exactly three triangles and one pentagon, and go on vertex after vertex. So you can only have to look and worry about one vertex at a time.
Okay, why don't some others go ahead and share some video as well? So join Tori and Diane. I think Bridget had raised her hand earlier. Bridget, if you want, you can go ahead and turn on your camera when you're ready.
Okay, anybody else? Can I see some of your constructions going on? Just make sure that it's hook to loop, loop to hook.
Do we have any brave souls out there? Come on, guys. Yay! All right. Bridget, Christina, yay!
Hang on, Bridget. We, at the top of this, okay, show me what you're doing. Show me, Bridget, okay? Put a pentagon, and then those, yes, and put two more triangles at one vertex. Okay, so you have one vertex done. Show me that first vertex that you've done. Okay, super. Put a third triangle. Yes, exactly. Yes. Put it there. And now look at the next vertex. Next vertex of the pentagon, and build 3 triangles there. And then move to next and build 3 there until you went all around. Okay, Christina, can you show me what you're doing? I can see your beautiful face, but not see your work. Can you raise it up, the construction? Okay, wonderful, but it's not what we really wanted at this moment, because first of all, you need to have a pentagon at the base, and then we do the triangles, right? Where are my triangles? Okay, here. So we are putting triangles, like we are putting first triangle, then we are putting second triangle, and then, hang on, we are putting a third triangle, like this, and closing this, hang on, here, closing this. So here we have a, hang on, oh yeah, okay. So we have 3 triangles and a pentagon in this vertex. So now we're building next vertex here. 2 first triangle and some more triangles at the same vertex. Wonderful, yes, very good, Bridget, yes. So we put 3 triangles like this, and so on and on and on until we get all around. Yeah? Who is Robin here? Robin, you're using wonderful. Are you using hexagon or pentagon? Yes, good. Hexagon you're using, but that's still okay. Okay? And Christina, show me your work. Okay, wonderful. Oh, so many of you, wonderful. Yes, super. But once you go around, you cap it up with the next pentagon, right? Is everybody done? Show me. Yes, I can see very good work for Christina and for Robin. Robin is done, I think. No, Robin is not done yet, right? Because there's, and who is here? Diane. Oh, yeah, she is adventurous lady. She did that with the isosceles triangles. Wonderful. I'm happy that one person did that. We will talk about it in just 1 second. So everybody is done? You can see lots of people still working, so I'll still wait a little bit. Because next exercise will be to compare those 2 structures that we made using pentagons. Okay, so let me have a look. Everybody has finished. Bridget, did you put something on top? You need on top, because those on top need also a pentagon, right? Yeah. And Amanda, will you show me your work? Beautiful, yes, you are on your way, yes. Fantastic. Just finish those triangles around and put something on top. Put whatever you were using at the bottom. I think that maybe you are using hexagon. But you don't flap any more triangles on top. On top there goes the same one that's at the bottom, because each vertex has to have 3 triangles and a pentagon, right? So you can see that now you build something quite complicated by following a very simple rule, right? Looking at the vertex. Now let's talk about those two solids that we made, right? You made this, and what was the name for this? Anybody's on the speaker? Nobody. It is a pentagonal prism, right? Now, what is this? It is something similar, but not quite the same. Now, what I would like you to look and tell me, what are similarities between those two structures? What is similar between them? You can type into your box or just give me some ideas. What is similar between this and this? Or maybe anybody wants to speak up. Okay, anybody going to tell me? You know, Bridget, you are saying something, but I cannot hear you. I don't know if everybody can hear you. Maybe you have to unmute something. Okay? Yes? Yes? Andrea, can you help? Put somebody on?
It's hard to hear, Bridget. I think our best bet, because I'm hearing some feedback from people with microphones on, so I think probably using the chat box, guys, is our best bet.
Okay,
so go ahead and just utilize
the chat box. Okay, guys. So tell me what's the similar between those two things. Or should I tell you?
We've got some people typing.
I'm not telling.
She's waiting. She's patient.
Well, wait.
Diane is typing. She says the pentagonal sides have the same surface area on each.
Well, okay, yes. So there is a pentagon at the base of each of those solids. What is different? That differences are easy.
No takers yet. Oh, Bridget's typing. Diane, oh, we got a couple typers.
Let me just look at this. Okay. Okay, stepping up. No?
Oh, Diane said the sides.
So the sides are different, right? Because here there are triangles and here there are squares. Okay, is it the same number of sides? No, you can just do this. Yes. No. What other things are similar or different? What other things are different?
Bridget says the vertices are not congruent. Tanoy says height.
Okay, the vertices are not congruent. Do you mean they are different? Okay, let's talk about the number of vertices. Is it the same or different?
Tanoy says different.
Okay, let's
Amanda says different. Diane says same.
How many vertices here? 5 up here and 5 down there. It's 10. And how many here? 5 up here, 5 down there. 10. So it's the same number of vertices. That's quite surprising, right? Because you would have thought that it's more here than here. No. It's different numbers of edges, different number of sides, different number of things. Also, I want you to have a look at those pentagons. Here, those pentagons are just have the same orientation. They are just shifted like this, right? They have the same, like you could superimpose one on the top of the other. Hang on, I have to keep it like this. Now, if you look at this, the pentagon here is like this, and the pentagon on the other side is rotated. So here you have a translation and rotation of the pentagon. Now this one is called Pentagonal Prism, and this one is called Pentagonal Antiprism, because they are related. So now here I gave you the idea about solids that you can build by using simple instruction, and they are very different from whatever you were studying before. But it's still fun. Children make those structures very readily. So your students will make them too, and they will be very happy because it's more complicated than just this, right? Okay, let me go now to change this. Okay, so let's now do the next thing. How about I ask you, so here is the view, and here is comparison. So here is pentagonal prism and pentagonal antiprism, right? Now, if you make, do we want to make more antiprism? Just one so that it's like, that you can understand that. How about you make, now you made pentagonal antiprism. So how about you make me a square antiprism? So you will use basically the same idea for the sides. There will be 3 triangles, and at the base there would be what? A square. So you will use square and 3 triangles in each vertex. Just to practice, so that it's a little bit better integrated and it comes to your vocabulary.
And a few other people, please feel free to share, like, let's see, Mia, Pinoy and Sheila, Gonzalo. Feel free to jump in.
So here you have to have a square, then three triangles, kind of triangles building the sides, 3 at each vertex, and then on top there would be another square. Oh yeah, very good, Bridget. Yes, that's what we want. Show it to me once again. Okay, and where is the second square? Okay, can you put it square like on the bottom? Oh yeah, not yet. Beautiful. Yes, exactly. And Diane, show me yours. Yes, exactly. Can you see how those squares have orientation like this? Like one list like this, right? Can you see they are not parallel? They are parallel and twisted, like rotated a little bit. Beautiful. Okay. Now, before we go out of this subject, I wanted to also show you one thing that Diane made it already. You do not have to use the isosceles, the equilateral triangles. You can use isosceles triangles, right? So this is also antiprism. And this one, you can compare with this. You don't have to use the squares and the equilaterals. You could use those, because that way you expose your students to a more variety, right, of things that they can do. Okay, so now I just want to give you one more bit of information. Hang on. This is what it looks like, and you all made it very nicely. And now I want to tell you that this property, that each vertex is the same, but not all the sides, the faces don't have to be the same, but the vertices have to be the same. Those kind of solids, those type of solids, are called Archimedean solids. So all those that we build right now, those prisms and antiprisms, they are Archimedean solids. But now there is a question to you. How about pyramids? Can you build yourself any of those pyramids that you see on the drawing? And question is, are those Archimedean solids? So do they have all the vertices the same? And I want some answers. Yeah, so do we have some pyramids already done? pyramid at all. And now I want somebody to volunteer with explanation and answer. If pyramids can be classified as Archimedean solids, so such that have the same vertices. Can you use this idea of building by the vertex to build pyramids? Anybody volunteering here?
Robin looks like she has a pyramid.
Yes, okay. Can you put on somebody vocally so that we can hear the answers?
Let's see, Robin. Your microphone's enabled, Robin. I don't know if you might need to turn your mic volume up. Do you know if it works? If you go to the microphone at the top, push the drop-down arrow, there's an adjust microphone volume. See if we can get it to work. Gonzalo has raised his hand. Gonzalo, feel free to...
Yeah? I just want some answer from a participant. Is this an Archimedean solid?
I'm enabling Gonzalo's microphone.
Gonzalo, speak up.
Not hearing anyone. Here comes somebody.
Oh,
there we go. There's Gonzalo's prism. Awesome. The pyramid, not prism, sorry.
Okay, Gonzalo, so what are you saying about that pyramid? Is this Archimedean solid? So say yes or no. I cannot hear anything. I cannot hear anybody. Andrea.
Yeah, I think the microphones is probably not the best way to do this. I think you all need to use the chat box or shake your head yes or no if you're on video. So
okay,
Gonzalo is
this Archimedean solid. Yes or no? Nobody is doing anything with yes?
Yes.
Okay, you say yes. Okay, so this means that every vertex is the same. Is this vertex the same as this? This one has what? A square and two triangles. And this vertex has what? 4 triangles. So this is not an Archimedean solid. Because this vertex is always different than those vertices. For every pyramid that you want, right? If you take any other pyramid, it's always this is different than this. Actually, only in this pyramid, this is all the same. But in this one is not. So pyramids are not Archimedean solids, and this little rule that I gave you to build will not apply to pyramids, okay? Pyramids are a little bit special. Now, you know, I had a little bit more work with pyramids, but I am looking at the clock here, and it's going a little slower because the interaction is not that fast between me and you. So what I will do, I will now skip a few slides to get to the more relevant information for you. And if we have time, we will go back to those pyramids or maybe some other time. But I need to skip, okay? Because I think that there will be more important information for you a little more. So here you are, we go.
Here, Aniceta, there's a question from Christina.
Yes,
for it to be a solid, does it always have to be the same amount of vertexes or vertices?
The same amount as what?
It says, for it to be a solid, does it always have to be the same amount of vertices?
I do not really understand this question. The same amount of vertices as what? You know, for it to be a solid, it has to be you know what? It's a question that I don't quite understand, but I'll keep it in mind. In just hang on for this for a moment, because what I will do is I'll do this modeling thing now, and then I will come back to those pyramids again, so that we can inquire about when it's possible to make pyramids, when it's not. Maybe that will answer your question more fully, okay? But I want to go to the modeling because that is very important for you to know how to model those problems for the solids. But we'll come back to that subject, okay? So how? Modeling. For modeling, it's good to kind of use like an excuse Euler equation. Euler equation joins together number of faces, number of vertices, and number of edges, okay? And it's a very simple relationship. And for that, we will need to count number of vertices, number of edges, and number of faces. And now how we could help a vision impaired child to do it? Well, let's take something simple like that. I have gotten myself those jello kind of things from dollar store. And what you do is you just put it on the face that have been counted. Okay? So that way you mark what you have been counted, and that helps vision impaired child to go ahead. Of course, you don't have to use this, but it's very easily available and it's not expensive. Whichever shape you have, it's good. You can also take a marker, like those dry erase markers, for those that have low vision, and just write on the face. You can erase it later like this easily, right? So that's the way to mark it. Then in your kits, you have those pouches, okay? Take out the pouch and take any structure, any solid that you have right now. So now those little orange ones, I designed to put them like this, like right in the middle, because it will catch any of those Velcro. So again, you can mark any of those edges, and the child will kind of go around and mark whatever is counted. Of course, your goal is for them to absorb this shape of that structure enough for them to not use this, but kind of visualize and conceptualize and be able to do it from the principle. But beginning could be this. Now you have also those white pieces, like that. They are longer. So what you do, you just bend it like that in half, and you just stick it to the vertex. Anyway, it'll stick. It will stick somewhere. Okay, like this. Okay. So you see, it's fairly easy then to go around and count or mark what has been counted, right? Okay, so here it is. So once we counted and made note of how many vertices, how many faces, and how many edges any of those structure has, then you can use this Euler equation, right? You have counted it. You now know how many of each, and now you put it to the equation. So the number of faces add to the number of vertices and take away the number of edges. And what comes up is that this number for any solid is 2. Okay? So now you can use this as either checking with your students to check that it's true, or you can have many solids and then find the relationship, find the pattern, right? So you can use it in many different ways, whatever is the level of your student, right? Now, question to you: if we had cylinder and cone, does Euler equation apply to cylinder and cone? We had the number of faces, number of vertices, and number of edges. Does that equation hold for cone, and a cylinder. Give me your shake.
We've got some people typing in the chat box, or you can shake your head.
And why not? And why yes? Could you write down something for me? Why not? If you think it's not, write down why not. Why does the Euler equation that relates number of faces to number of vertices and number of edges would or would not apply to cylinder and cone? Any answers? I cannot see anything, but I am not very good.
I can read it.
Okay, can you read it for me? Anything?
Yeah, so we have Tori. She says cylinders don't have a defined vertex.
Yeah, because cylinder has a circle, right? So where is the vertex of the circle? Okay, and the same for cone. Where is the vertex of the circle? Though that equation applies only to structures that are made of polygons, something that has vertices, right? Okay, very good. I'm very proud that you understand that. Now, labeling solids. That's also something that could be very important to you. Now, what do we have here? I gave you those little pieces of Velcro with colored thing. This is I just gave you one or two, I can't remember, I think that I stuck two together. This is very easy to make. I made it with Velcro and electric tape. So you get yourself electric tape and Velcro on top and bottom, and you can write on this with markers as well and erase. So if you use a light color, you can make your labels yourself, or you could use your braillers or whatever you have to use and put Velcro on this. So you can see that you can write and then you stick it to your vertices and you can label anything. Now I will now show you some ways, like my slide, and you can then, I will invite you to make your own, okay? So that you have a little bit of practice. But first have a look here what I did. So you can put n of vertices, you can put on edges, right? So here, if you make a tetrahedron, which is this simple triangular pyramid, make this one and label all the vertices. So use those little pieces of Velcro with the color, use your marker and cut that, that's why you need these scissors, cut that, put A, B, C, D, put them in so that you can have a label. So you have a model of your triangular pyramid with all the vertices labeled. I would like you to do this right now. Okay, everybody done? Show me some. Like raise your thing that I can have a look at your beautiful work. Super, Diana. Wonderful. Yes, that's what we want. A, B, C, and D should be somewhere, right? D. Good job. Yes. A, B, C, D. And so you can see that you can use this to actually, if you have any problem in the book or any verbal, you can just model. You can model more than that. Next thing I'm going to show you is how to make connectors. Okay, so here it's also in your little pouch. You have some paper clips that have Velcro attached to it, and you have some straws. So take out a straw and two Velcro, like one hook, one loop for the paper clip. So what you do is like, you can see what I did here. You have one paper clip and you just shove it into the drinking straw. And on the other side, you shove a different Velcro. So if you had loop here, you have hook here. So then you have a sticky rod, right? Now, if you make lots of rods like that, you can stick them together and you can make triangles. They'll stick. Okay? So now you can cut those straws to any length you want and make triangles. Now, how is this going to be used to actually model in 3D geometry? You could put those triangles, if you cut them. So here I have something that I already made. I have a cube that I labeled the edges, and I made a triangle inside that will model some problem. And now you can open it up. You can have inside. Okay, you can have your student touch it. Okay, this is the most difficult one because it doesn't have much Velcro to stick in here, but still it sticks. So you can see that you can now model some distances in the solid, some problems that are word problems with building appropriate triangles, right? So next, what we are going to, I'm going to show you a few more ideas of what else we could do with this. Why does it go? Oh, because I'm using my other computer. Okay, here you could also, instead of doing it with straws, you could also, of course, use the markers to draw, right? So you can have either. For some students, it will be good enough to draw, but for some students, they need to touch, right? So you can put that straw here, for example, if you need. But that's just ideas that you can use the markers, you can use the straw. And also here, I have the same work on the cylinder, and here is a little, another trick that I had. If you just shove one paper clip, just a paper clip, to the straw, you can use a magnet and it will hold it too, like you can see it on the drawing. I didn't give you magnets for reasons, but you can get any little magnet and just a paper clip, and on top of it you can kind of secure that straw by the magnet on top of the through the plastic. Okay, so now what are we going to do? I will invite you to do the following. I have a little problem below in the next slide that I would like you to, there are two problems. You pick one and you make a model for that problem. So you have to label the vertices, you have to make the triangle that is appropriate. The problem has dimensions. So you are not going to be measuring anything, because you can just write on somewhere that it's a model. So it doesn't have the right dimensions, but it has the idea, right? So I want you to label vertices, points, show the distances for one of the following problems, right? So here are the problems. Cube ABCD, A prime, B prime, C, D prime, has an edge length of 3 inches. Say. Now, what is the length of the cube's diagonal? So what kind of triangle would you use to solve this problem, right? Because you will use some Pythagoras triangle that will be right angle triangle, and then, so you need to show, I need to show the diagonal, and what triangles would you use? You can put it inside, but you can also take it out and put it inside, things like that. Or you can use another problem. You could use a hexagonal pyramid, A, B, C, D, E, G, O for the top. That is 17 length of the hexagon edge, height with a height, so you are given the height. And then you are given the height of the triangle. And what is the height of the the length of the hexagon you are given, and you ask for the surface, for the height of the triangle. One thing here, if your straws are too short for this, for example, because I know that will be, what you can do, you take 2 straws, you pinch one, like pinch, like this, and shove it to the next. And you have 1 long straw. What I also did sometimes is I use this electric tape, and I just wrap it in the electric tape. So it's 1 long, nice straw. But you don't have to. You can just use it like that. So get busy with one of those problems and illustrate it. Make the appropriate triangles using those Velcro paper clips with Velcro and the straws. And you can also write on your structure, label the structure. So I'll give you a few minutes now to make it, and then we will share observations and concerns and ideas, okay?
Aniceta, Tori had a question. Did the letter labels come in the kit?
If what? Once again?
Oh, the letter labels. I think we saw someone that had letters on their labels, perhaps.
No, what you have in the kit is Velcro with some color on it. I put that to each kit. So what you need to do, you need to cut that into smaller pieces, and with your dry erase marker, write your letters on it, like that, right? I've done it here, so I cut it and I put letters on it, right? Those are erasable. Those are erasable. We could, because then if it's not erasable, it's waste of Velcro, and it's really expensive to just throw it out. But you can erase it quite a few times. Okay, so yeah, I can see the Bridget is making a pyramid. I guess that you will be needing to elongate your straws, so you can do it like this. Okay, Bridget, stick it in. I can see you. Just stick it in, yes. Okay, so this is your thing for the. Did you put the clips into those straws? So first you need to cut it like little. It has to be a little shorter than the actual height because you have to allow for this. And then you fix 2 paper clips on top and bottom, and then you need to build 2 more of those straws because you need a triangle, right?
Christina has red straws. Are those the same?
No, you don't cut those yet. No.
Oh, good. Kate Waller has joined us from Pinellas. Let me enable her video.
Okay. Well, let me just. I haven't made it myself.
And Tori and Christina look like they have.
Okay, anybody has some problems with it, or anybody has some comments already to share? Everybody finished? I haven't got a good feel for how quick you can do this, guys, because it's, if I don't see you, it's very difficult. Okay, that's good. So you have the, we have the thing. Now, how do we do with the?
Diane said she's ready to share, but she's not sure if she did it right.
Okay, cool.
Diane.
Okay,
Diane, she's smiling, holding her squares.
Yeah, wonderful, yeah. So you showed the diagonal, right? Now, but in the problem, I give you the length of the edge. So you need to, this is a given, okay? So you can even use a different color of straw for the given, okay? And then you need to build a triangle that holds those three together, right? And the problem with the problem that has the hexagonal thing, it's a little bit more complicated. I just kind of looked at it now and I said, oh my God, it's like a two-step problem. But never mind, I mean, you can deal with it. You are good teachers. So what it needs to be done, it's, you know, I'll just quickly made it. I should have made it earlier, but still.
Diane said she's sorry, but she's not quite understanding.
Diane, she's not understanding, right? And what you are making, the diagonal, right? Okay. So you have a diagonal here, like this, say. So I will draw the triangle that you need. You need this triangle here at the bottom, and then you need this. So you need the triangle at the bottom. You see, this calls for some strategy of math already, right? So it's like it's not so easy for me to teach you all the way because I was kind of thinking that, okay, this is the triangle that you need. Can you see this, Diane? Okay, the triangle that is diagonal of the cube, then the diagonal of the base, and then the edge. And that is your right angle triangle that you need, right? And now you can even open it up here once you have this properly done, and your student can actually touch it, and you can even take it out and put it. And then this one is what I gave. This one is what you have to calculate from as a diagonal of the square, and then this. You know, I do appreciate that this is a problem, maybe not for higher grades in elementary. The other one would be also for higher grades in elementary, maybe even secondary. But the idea here is that you can use those straws with those connectors to show any distance and any triangle that you need to show. And that's the main point. And if you have trouble with the actual understanding of the triangles, that is a little bit different, because then you will be guided by the math teacher and everything. But your contribution will be showing it off. Any other questions or concerns? No? We can go on ahead, right? Okay, so next thing that I want to show you is orientation of lines. How to show that. For this, in the kit, you have some, I call them Velcro rods, those red Velcro rods. They are very flexible. And what you can do with them is to show directions. So you basically accentuate the directions of lines. So for example, if we work in a cube, you stick it to the edge like this. Okay? It doesn't have to be cube. You can work also with your pentagonal prisms. Doesn't matter. I'm just showing it on the cube. And now this one, these two edges are parallel. So for a child that doesn't see, it is probably easier for them to actually have it accentuated like that, right? So you can stick it, yes, wonderful. Or now, could you show me two perpendicular edges? Wonderful. And now two skew edges. Skew are ones that don't cross. Yes, they are in two different planes. So they are not parallel and they are not crossing at all. Right? So they are skew edges. So you can do this. Of course, in the cube, it's easy, but it's a little bit more difficult in the bigger structures that we are not going to have chance to build right now, but you might come across them. So here is one more little exercise for you. How about you build yourself this simple triangular pyramid, which is a tetrahedron, and show me different pairs of skew edges in this. Okay, good. Yes, Amanda, brilliant. And Bridget, good job. Yeah, okay, so it's one. So how many do you think you have? Pairs. How many pairs like that? I don't know the answer. I mean, I didn't even think of that. Okay. So how many do you see? Quite a few, right?
Tori has 3 on hers. Bridget has 4. Anybody else? Perfect. And Diane Tonoy says 3. Diane says 3. Robin says 2. Christina has 6. Kate Waller has 6. Sheila 3.
Okay. We're going to have a contest later on.
Kate and Sheila, feel free to share your video as well.
Yeah, wonderful. Okay, but you get the idea, right? That there are many pairs, and you do very well in actually finding those. This is an easy one, very straightforward, because you can see this. Okay, so now you can put away those Velcro rods, and what I want you to do is to get into the other rods. Those are those rods, right? So how would you use those to show diagonals? So how about you build yourself a cube? Build yourself a cube, once again, empty cube, and use those to show diagonals. And I want all 4 of them at the same time. Okay, yeah, wonderful. You got the idea. Very great. Wonderful. Yes. So, what are we saying? You can see that you can put all 4, right? So we can see that they cross in one spot, and there are 4 and such. So, and here is one more trick for you, for students who need to touch. So here it's how hang on this way. Yes. You can use, here I put just one, and I opened it up so that it wouldn't fall out. I used this white Velcro to hold it, right? So then it's open and your student can actually probe it inside. When you have 4, you can do the same. You just have to use 2 of those, right? To secure, when you're opening, those 2 on top could fall out. So you just secure them with this white piece of Velcro connector, right? So try to do that. Try to, once you have 4, try to open up the flap, but keeping the secured with the white piece of Velcro. So you pick which one you want to open, and on this face you have to secure the tops. Great. Now, did you open? Yeah? Yeah? Yes? Okay, good. Now you can do also this with 4. So you put all 4, and then you have to secure 2 tops so that the 2 ones don't fall out. No, yeah, wonderful. Yes, Amanda, that's how you would do it. Yeah, yeah. Well, all of you can figure it out easily. It's not that difficult. Yeah, wonderful. So, but I just wanted to do something now that we don't really do often, because when we talk of diagonals, we just use a cube. But how about you build yourself back, you just dismantle that cube and build pentagonal prism again. Pentagonal prism. Build it again. Take out those Velcro, take out that thing. Okay, yeah, so get out that cube, dismantle that cube and do the pentagonal prism. Okay, and now I want you to put as many diagonals as you can see into this pentagonal prism. Okay? How about Christina? Are you doing this pentagonal prism too? I can see you. Okay, where is the pentagonal prism? Yeah, okay, super. Is this pentagonal? This is a pentagonal pyramid. This is a pyramid. I want a prism. The prism is, I show you, this is the prism. This one. So make one like this and put some, as many as you can, of diagonals. Wonderful. Okay. Yes, very good. Bridget doing very well. Lots of. So what you can see now, what's the difference between the previous scenario for the cube? Here, where do you see where they cross those diagonals in the pentagonal prism? So now you can see that they do not cross at the same place, right? So it's not like the cube at all, right? It's much more complicated. And that's what we want. We want cases that are a little bit more complicated than just simplest cube, because that's what people always use, just a cube. Wonderful. Yes, Amanda, yes. And Catherine, I think that you need a few more, but you can just stick them more. And this brings us to next problem. Here, and the cubes show diagonals, build a hexagonal, build that. How about now you do And next exercise, build me a hexagonal pyramid. Okay, so you have, yes, I can see, Bridget, you already have your hexagonal pyramid. And show me the diagonals in the pyramid. Okay, any comments, any conclusions, any ideas? What's going on? That's a good exploration, right? So what is the... Can anybody comment? Or nobody has a microphone. Can you just type something for me? What are you seeing? What is happening?
We have Bridget typing.
Yes, Bridget? What are you saying, Bridget?
This is where we also test your touch typing skills. How fast can you type? Just kidding.
Okay, so what is Bridget saying?
Now we have multiple attendees typing. It takes a second.
Okay. Very
The lag time, I think, is the hardest part about webinars.
Yeah.
Okay, so Amanda says the red straws are running along the edges of where the triangles meet.
Ooh.
And Kate Waller says they cross at the top like a teepee. Bridget says with the hexagonal prism, they aren't horizontal, they just go against the sides. And Diane says there are no diagonals.
Diane says there is no diagonals. So we have very many ideas. You know what? This brings us to actually definition of a diagonal, because in a cube, when people say in a cube, they say, okay, it's a line that goes to the opposite vertex. Period. Simple. In a pentagonal prism, it was a little bit more, but we still could do this, you know, kind of shoot somewhere where we are not sitting. But in pyramids, we are coming into very different ideas, but we have not yet defined what actually diagonal in a solid is. So let me just go and say, what is diagonal? Definition. Definition of diagonal is, now listen, ladies and gentlemen, it's a line that joins two vertices but doesn't coincide with a face and doesn't coincide with an edge. Okay, you heard it? You have to have joining two vertices but not on the face and not on the edge. Okay, now go back to your work and see how many diagonals do you actually have in this pyramid. Not on the face, not on the edge. Just through the body. So what, Bridget, what are you saying? Show me your diagonal. Is this a diagonal? Because it's...
Bridget says 0, Robin says 6, Christina says 6.
Hang on, let's go one by one. Bridget, show me yours. This, okay, do they coincide with the face? So is it a diagonal? No. Get it out. Take it out. Okay. Now, Sheila, show me yours. Okay, where are they lying? Do they coincide on the faces? Do they lie on the edges? Not the diagonal. Take them out. All of them. Okay, anybody else have some other ideas? Here, Catherine at the bottom. Does it lie on the face? Does it lie on the bottom face? Yes, it does. So it's not the diagonal. Take it out. And here is Christina. Where does it lie? Does it lie on the edge? Does it lie on the edge, Christina? It does. It does. So take it out. Okay. So you can see, Christina, take it all out. And who is here? Robin, take it all out, Robin, because you have it all on the edges, right? It all coincides on the edges. It's not a diagonal. If it stays on the face or if it stays on the edge, it is not a diagonal. So what we are coming into is that pyramids do not have diagonals. Can you see how funny it is? You know, we always worked in a cube and we perfectly knew what the diagonal was, right? Because it was just, woo, to the next vertex. But it's way more complicated than that. And why don't we talk about it, right? We need to talk about it and show it, right? So here is diagonals. I think that I have a few more slides on that, but no, I don't. Measuring 3D solids. Now, measuring distances is going to be kind of straightforward, right? You would have to have a ruler and, you know, measuring is going to have an error here and it's not much of a measurement. I mean, you could measure, of course, but it's what I wanted to show more is measuring volume. So how do I measure volume? Is the following. I have those pieces. I didn't send it to you because it would have been too much for me to cut. But those are those packing beans, you know, peanuts, right? Those are the squishy styrofoam peanuts. And I cut them, you know, the smaller the better, but they are very, very light. So what do I do is I then can measure the volume. For example, if I wanted to measure volume of this pyramid, what I would do is I would put all this here, like this. Okay. Don't use beans, don't use stones, don't use anything else because it's too heavy and the Velcro will not hold. I tried. And it's you know, this has to be really light for the Velcro because it's quite a bit of volume. So there are two things that we could do here. It's almost equivalent pyramid and prism. This is a little taller, but just a little bit. So what I can do is to show that this volume of this is 1/3 of this. So what you do is open this one and just shove those peanuts here. Like this. Okay? Oh God. Hang on. Okay, so I put what I missed in. And you can see that it is almost 1/3. Can you see? Right? So you can actually show quantitatively that it's 1/3. But you can do one more thing. Here I got and then that you have also to find it on the internet. I found a cube tray that is 1 inch cube. So the tray is a 1 inch by 1 inch by almost. It's a little bit, but it's almost. So now what you can do, you can actually directly measure by putting it back to that tray, right? And then you imagine, I don't want to make a mess here, but you just put it in, and however many cubes you filled in, that's how many cubic inches there is. It's a very conceptual and very straightforward way of measuring. You are lucky here in US that you measure in inches, in cubic inches, because here in Canada we measure in cubic centimeters, and they are way too small to do that. It's just they are so tiny that it wouldn't work. But for you, this concept actually does work, because you can just pour it in and you just make sure that it's not. It makes an error. It's not perfect, but it's surprisingly well. With an error you can actually do this. Also, this thing is not in your kit, but I just wanted to show you that we do have a very new kit of cylinder and cone, and they are the same height, so you can actually do the same exercise that shift those here. And the kit that we have is having two different cones and two different cylinders, and they have the same height. So here you can actually have this exercise for both, right? And also for surface area, this one is also good because it shows exactly the surface, the side surface of the cone and of the cylinder, right? So it's a direct relationship to the shape of the lateral surfaces. So here it's a measurement of the volume, right? Like direct measurement of the volume. Okay, so here it's the cube and the tray, and prisms and pyramids. You can compare them like that, and the same with cylinder. Now, oblique solids. What are oblique solids? Like we work with a cube, but we never really work with anything that is like skewed cube, right? Not quite under right angles. So it's not a cube anymore, but it's like a prism. So here I wanted to show you. Okay, so if we have a cube, what I did is I made a cube like that without two faces. And then here I have foam. I have dimension of that foam here as well. Here. So the dimension of those squares are 11.2 centimeters. So I have lots of them, and I had stuck such that here is an inch. Okay, and here it's an inch. So here it's 2 inches of foam. Okay, and here it's another 2 inches of foam and a little bit. So when I put it all together, I put it to that cube like this. All right. You see? So you have a 4 and a bit of cubic inches, right? And now I also have something to measure the height of this. Where is my little height measurement? I'll show you in a moment. Just one second. Where did I lose it? Oh, yeah, here. This one is a very simple thing. This is a paper. I took the little measuring tape, paper measuring tape from IKEA. You can do anything else as well. And I just made a little tube out of it. Then I have my old good paper clip and straw. So I put the paper clip in and I bend it like this. Can you see? And I shove it in. And now what I do is I put it like this here. Hang on. Like this. So this measures the height of this cube, right? So now what if I wanted to make that cube oblique? So what I will do is I will I cannot move it right now because it's full, right? So what if I removed 1 inch, like this, put it in, and then I will make it oblique. So you can see that the volume of this cube got smaller. And also the height of it got smaller. Can you see that? So height is not, here it was 4 inches, and now it's just 3 inches. So you have a very visual illustration of the volume changed. The volume is smaller because the height is smaller. The base is the same. And now if you remove more of this, you can remove more, okay? So the more oblique you make, right, the smaller is the height. Now the height is even smaller. I probably should keep it in here. Okay, so the height is smaller and the volume is smaller. Because you can see that now height is just 2 inches and a little bit. And so on, right? Until you can come to actually minimal volume, which would be like this, 0. So this you can illustrate how the volume changes with changes in height. So here is a little sequence that I'll show it to you again, right? So you have those cut pieces of foam, and you know, you just have to have a stack of those foams. You have the paper little tube with the measurement, and the paper and the drinking straw and Velcro. And that's how you gradually show how the height changes and the volume changes, because there's fewer and fewer of those foams that can get in. So it's visibly volume is changing, right? Now, another way of showing oblique solids is doing it like a little bit differently. And it's, you can do it yourself as well, but I'm not sure that you want to do all of it at this time. Here I have already paper clip, like the drinking straws, and I actually even didn't bother with paper clips. I just put Velcro on edges like this. So just clip them to this, and you'll add the next here, 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 and here. I have to do it on the bottom because it won't stick. I do it like this. Okay, so you have a solid, and now you can do this, or do this, do this. You can see how flexible that is. So you can have ways of showing other solids other than those really regular ones that we do with Geometro. Because if you use just straws and just 1 or 2 polygons, you have much more flexibility to change, to twist, and so on. So here is more ideas of you know, how you can twist. And you can, by the way, remember how we built those Antiprism in the beginning? This is what it is. When you actually twist this like this, this is what you have. You have the same Antiprism that you built in the beginning. Hang on, this one here. Okay, until you actually get back to 2 pyramids. And you can do the same with circles. So to do the same with the cylinder, and then you can twist it, and you can become two cones. Okay, so how much time have we got now? It's a half an hour. Okay, good. So how about we will talk about nets, because that's also something that you might be interested in. Now, cube. How many ways there is to decompose cube into a net? Anybody knows already? So here is an exercise that I do usually in a classroom or on a workshop like today, is that we would build a cube. So if you build yourself a cube, then you can decompose that cube and make a net. So we would decompose, and then somebody who has a net would go to the blackboard and draw the net. And then if somebody has a different net, would go to draw a different net, and so on. And only different nets go on the board. So I did that exercise with grade 2 children, like a general classroom. And it was fascinating because those kids were just very good. They were not any worse than teachers to go and find those different nets. But it gets harder and harder as you go along, because also you have to recognize nets that are flipped or rotated. So it's a very good exercise. Here is this exercise that I did in South Africa with teachers. So you can see that they are having a whiteboard and they are drawing those nets. It is quite difficult by the time you get to the kind of end of it to actually find a net that is unique. And there are 11 of those nets. So it takes a moment to actually find all of them. I invite you to do this, but because we don't have the communication between us, it's not that the easiest. We don't have Blackboard. It's not that easy. That's why we won't do it together. But something that you could do on your own, try to find all 11 nets for the cube. So how about now you just at least make a cube and decompose it to 3 different nets and identify which one it is out of those. Hang on, I will actually do this. So I will not show you those nets. Okay? So find, and draw each one on a piece of paper beside you. You can draw and kind of so that you keep track of what's already done and what's not yet. Okay, how are you doing? You have 3 nets. Oh, beautiful. Yes, fantastico. Very good, very good. Yes, okay, very good, very good. Yes, very good. Super. So you can see that, the first 3, 4 are quite quick. But then the more we get, the more difficult it is to find a unique one, different than what we found already. So this exercise is good, and it gets harder and harder as we go along. Unfortunately, we will not proceed because of the time, but you understand the idea. So here are the 11 nets, and then you can actually order them into a pattern. You can see how you can do it really a little bit more systematically, kind of find them out all one after another. But now there are some arrangements of the squares that are not nets, that cannot be put into a net. For example, if you put something like this, is this a net for a cube? Can you make a net? Can you make a cube out of it? No, because there is not enough squares, right? So this is not a cube. not a net for a cube. And there are other ways that something, might not be a net. You might have 6, but you might have them arranged in a wrong way. For example, if you arrange something like this, it's also not a net, right? Because if you try to fold it, you cannot fold. So there are arrangements of 6 squares that are not nets. So that's also important to show and to teach and get children to differentiate and find out which ones would work, so which ones are nets for a given solid. Doesn't have to be cube, can be anything. So this kind of exercise inspired a book that I kind of wrote. And, it's like a little exercise there where you have a number of arrangements and children have to color the ones that are good nets for a solid that's drawn on the top. So there is a picture of the solid and then there are nets. And while I worked with APH, they wanted to get that book into tactile drawing so that the children can, vision impaired children can also have this exercise. But what happened is that when I looked at my book, this one, there was this picture of the solid, like of a cube. And then it was, if you translate that picture into a cube, it is very difficult, you know it already, that it's very difficult for vision impaired children to actually tactilely read that drawing and figure out that it's a cube. It's virtually impossible. So what I did to actually translate that book, I came up with a new manipulative to help children understand where those drawings come from. So now I wanted just to very quickly show you this idea, although you do not have this material, but it's available from APH, but I want you to know about it and to know also conceptually what's happening. Okay, so for this, what happened, I made something that looks like this. What is my next slide? Hang on. Oh yeah. This is the whole set, but I just show you first just the cube, how the cube works. So here is a model for a cube. It's very flexible. So what I do is I put this with the help of the teacher. So actually the teacher puts it on the cube like this, right? You just overlay it with a cube. And then you take it out of the cube. So the student has some idea that it's the same. And then you keep it like that, and then you fold it like this. And now it becomes a drawing of the cube. Can you see the drawing? And you can have the drawing like that, you can have the drawing like that, you can have the drawing like this, and you can have it the other way. Right? So this is the idea, is that cube, to make it from this to flat, because images on our retina are flat. So what you needed is something flexible that will make it flat. So once you make it flat, you lose the angles and you use the length. So it's all different anymore. It's not the same anymore. So, and it gets even more complicated for the pyramid, because if you have a pyramid, to make it actually flat, you can see that there are red stickers on it and a green in the back. So the green has to get a little shorter and the red ones have to get a little longer. And then you can actually make a drawing of the pyramid. So those models are to give some kind of impression to the vision impaired child how it's so complicated to make a drawing, because our retina is flat, so something 3D has to be made flat, put on our retina, and our brain interprets it and undoes it to make it 3D again. So it's our brain that makes it 3D. We do not see it on our, signal on our retina is flat. And when we draw it in perspective, it's also flat. So that's what it is. I have now a few more slides to actually go through it once again so that you kind of have another, if you didn't get what I was showing. So here is the set, and there is one more thing that I'll show you. Cube, you can see how that cube doesn't have all the angles, right? And the photograph even, if you take a photograph, it's not right angles anymore at all. And this comes from perspective, right? Because in perspective, parallel lines actually coincide, like diverge. So, and it's not, in reality, they never cross, but in perspective, they do diverge. So this drawing of a cube, you can draw it from different perspectives, like 1-point perspective, 2-point perspective, 3-point perspective, and it stops to look like a cube more and more. Like it loses all those features. So that is really simulated in those models. So I have 4 of those models, and they can be kind of put like this, then taken out, then elongated a little bit, and then put flat. Okay? And so it's once again the same thing. And you can do it both ways. And a square pyramid the same. You can take it out, you shorten the green, you lengthen the red, and you have a drawing of a pyramid. And you can do it the other way as well, right? So here is the kit. So in the kit also there is a book that I have. So in the book that you have a tactile drawing of the cube, and you can actually superimpose this on this. It's the same dimension. It's just something like this, right? So you can then kind of get step by step into this idea how it's changing, and then you would have the 2 that are smaller and 2 ways, and then we would go to the picture of actual nets. So here for the nets, there is also one more thing. This is metal, and you have those magnetic tiles, and they fit into this raised drawing of the net. And on each page, you have some nets that are good and some nets that are not good. So you put those in, and then you build them from Geometro. So this is like a step-by-step process to actually learn, how to make those nets and how to conceptualize them, right? And there are, of course, the books that are all the explanation and so forth. So here is the adaptation of the thing. And I have one more thing that it's not at all a product, but prototype. But I think it's very, very useful too. Here I try to show how come that we don't see the broken lines. So here is a model of the cube, and I pasted some texture. So there is rough texture, there is felt here, and there is smooth tape here. And here I made the same thing, the same slab that there, and they have slabs. So now if you put it flat, you can see that this is like a drawing, but it shows that you cannot see at the back, because the back is where the broken lines are, because they are broken because you cannot see them. Oh my God, this is falling apart. Because you cannot see them, right? Because they are obscured by those, once you put them, it would be like this, something, right? So once you put them flat, they obscure the edges. They obscure those edges at the back. So this is the conceptual understanding of the complexity of the 3D versus 2D, right? So here is a little pictures of all that. summary. So of course it's important to have to include dimensionality in the tactile drawings. Now, what time is this? It's 3:18. I am just thinking that maybe it's time to wrap it up, and maybe you have some questions or some comments. I will also, so cross sections, I don't think that we will do, although maybe I can just show you quickly. On a cube, if you wanted to show cross sections, you can use elastic and just do this. So you can mimic this section with the elastic, right? So you can cut that cube like that, and the cross section is square. It's a little bit difficult probably for your students to get the idea that this is a square, but we could cut it physically and then make an impression, and it is a square. And you can probe when it's a square what other shapes you can get, all with the elastic. You can use shorter elastics, or you can, sometimes I put a little Velcro on the elastic so that they stick to the edges. So if we wanted to cut a little corner like this, for example, you see, I would keep those with the Velcro. Velcro and paper clips and drinking straws are your best weapons. It's incredibly powerful. So you can use them, and I'm sure you'll have lots of ideas yourself how to use them. So maybe I will just skip this, and I'll tell you what we could do together when we meet once, because I guess there might be a plan for a day workshop, because believe me, we could do it once again and for the whole day, because there is more that I could talk about with you. So here it's more. We could play with this. We could basically have hands-on experience. Once I can bring some sets, you can get some sets, and for those of you who actually have students that would need that, it's already available from APH, you can get it. We would build platonic solids. Platonic solids will be built using the same idea that we started in the beginning, which is looking at a vertex. So we would then use this idea to bring all beautiful platonic solids. And this will give us strategy to build more than platonic solids. We would build more solids. Like you can see here, it was a workshop that was dedicated for building lots of different solids. And it's very pleasurable, and you could do this too. It's just that it's a little bit difficult you don't have all the pieces, first of all, but because it requires lots of pieces, but also it requires collaboration between people. And right now it's a little bit different setting, right? So we would do this. We would do the projections, like the shape, the projections of the shapes. This is a version for not vision impaired children, but I have a version for you as well, where you would do with a stylus. We could do that. And of course cross sections of the solids, because I was expecting that we are not going to be able to do all that. For those of you who teach high school, we would do cross sections of cone and cylinder, so-called conic sections. I don't know how many of you have students in the high school, but that's a very new thing that we could do as well with this new set. And in the end, I would be more than happy to give you a little story of how, once we build all those big structures, all those big nice solids, I would tell you how all this relates to science, how you can see a lot of art in it, and how artists get inspired by those structures. So what are the art images, art inspiration from those solids? And here also, I mean, we could talk about that video, because I have all that on video. So here is the link that you can use to access the thing. And I would be more than happy to hear your comments. And if you have any questions, any ideas, here is my contact. I would be more than happy to talk with you. Are there any questions? We have like a few minutes.
Yay! So if you all have any questions, go ahead and type them in the chat box. We have some people typing. Like Aniceta was saying, we do plan on next school year, we would love to have a face-to-face session with her and have a working with the expert that focuses on STEM. So Aniceta would definitely be one of our top choices to bring in. As you can see, somebody's hugging their Geometro here in this last slide, as you all will when you start using them with your students or if you haven't already. I think there were so many wonderful, fabulous ideas about how to develop geometric concepts using the Geometro and the straws. Wonderful ideas. When Aniceta had approached us with all these new things she was coming up with in the use of straws, Kathy Krumpleski and I were like, no! Why didn't we think of this? Such simple adaptations that make so much sense for our students. Yes, but for your low vision students too, this is an incredible tool to teach these concepts, not just for students who are Braille readers. Okay, so Bridget says, what a great idea. This is such a great way to work on math with students. Thank you so much. Woo-hoo! Diane wants to know, oh, well, she says thank you, and she said so educational and fun, and she wants to know where you are located in Canada.
What are you located in Canada? Very near Toronto, in Ancaster, like 80 kilometers from Toronto and 100 kilometers from Buffalo. So between Buffalo and Toronto. Easy. Yeah.
Cool. Mia says, I made the cube and the pyramid, but the other more difficult stuff she had a hard time watching and replicating. Thank you. It was interesting and informational. Lots of thank yous. Robin says, straws and Velcro are my new best friends. Definitely. Oh, Diane says that her boyfriend lives in Toronto, so she was up there fairly often. How cool is that? Toronto is a beautiful city. That's cool.
Well, I am really looking forward to, coming again, because although you're already expert in using for lots of things that you will encounter, but I am sure that you will, repetition is also good, as you know. So whatever you missed today, you'll have chance to do it again, and maybe you can have some ideas yourselves, because again, once you start doing it, you will have ideas, and you are very resourceful teachers, because you have to be. So I will be looking forward to get inspiration from you, because that's how I kind of get my ideas. It's usually from teachers who ask question or post a comment, and then I say, oh, I never thought of that. So I am really looking forward to more vocal interaction, because this is I am missing the contact with you, because it's like a little bit slower than it would have been in person. But I think it's a great idea, and I really admire Andrea for actually having arranged all that and having control over it.
All right. Oh, Amanda says, I had a great review of Platonic solids. I had a math course in college that focused on Platonic solids in art, specifically Salvador Dali.
Very good, very good. Fantastic. I think that it's a very good subject, because, people do use those solids so much that it's like never ending. You can always do something with Platonic solids. Yeah. And I can talk about, like, long time.
We can tell you're passionate about it for sure. Christina says she really enjoyed the instruction on the nets. It's a great way to explain those concepts. Yay, awesome. Okay, so guys, since we're wrapping up, I'm going to go ahead and put the survey out there, and please go ahead and leave your answers to these questions here. There's 4 questions and then an open-ended at the end. And thank you guys again for participating and going through this first type of webinar that we've ever offered. And I'm so glad Aniceta was brave enough to do it with us. I think she was the perfect candidate for it.
Well, that's a great experience. I've never done it this way at all.
And I'll let a few more people answer. Let's see. 29. They really love the straw and Velcro and paper clips. Such simple adaptations, again, tell you. And we did record this, so we will get this up as soon as possible. We kind of want to see how tomorrow goes as well. Different things may come up on tomorrow's webinar, so feel free to watch that recording too, or you're welcome to tune in at any time. Okay. Let's see a few more people answering the last question. And I will give you your, if you've already filled it in, I'll give you your closing code, which is pyramid. Pyramid is your closing code. Okay, we have 8 answers here. Another 9. Fantastic. All right, 10 answers. All right, so I'm going to go back to sharing. Oop, it'll let me. There we go. Thank you, everyone. I really appreciate your time and joining us this afternoon. And if there are no other questions, we will see you guys next time.
Yeah.
Thank you, Aniceta. We really appreciate your time and experience and all your knowledge.
It was such a pleasure. It was so nice. I really enjoyed this a lot.
Great.